So to compare functions asymptotically, we have three notations that we have seen. We can say first that g of n is an upper bound, that is f of n is O of g of n. If we can find constants n0 and c such that fn is below c times gn for every n bigger than n0. On the other hand, we can also establish lower bounds. We can say that f of n is omega of g of n if once again we can find constants n0 and c, but this time f of n is always above c times g of n for all n bigger than n0. And finally, we can say that the two are the same order of magnitude. So f of n is theta of g of n. If we can sandwich f of n between two multiples of g of n, so we can find n0, c1 and c2 such that c2 times g of n is always below f of n, which in turn is always below c1 times g of n, again for all n greater than or equal to n0. Now, very often it is difficult to come up with a clever choice of n0 and c to establish these relationships. Another technique that can be used is to use limits, right? So supposing we want to compute whether f of n is O of g of n or theta of g of n or omega of g of n. So we compute the limit as n tends to infinity f of n of g of n. This intuitively captures what we are doing this asymptotic behavior, looking at the function as a limit. So now we have several possibilities for the limit. So if this limit goes to 0, okay, then we can say that f of n is smaller. So we can generally see that f of n is big O of g of n. Okay. On the other hand, if this limit actually converges to some constant c which is bigger than 0 but it's a finite constant, then they are of the same order of magnitude. So we will have that f of n is theta of g of n. Okay. And if it diverges, that is if it becomes infinity, then f of n is growing faster than g of n. So we can say that f of n is always above g of n, so it is omega of g of n. Okay. And of course there is a fourth possibility, is that there is no limit defined. Okay, so this limit is, and in which case we can't do anything, but this is rare. So this gives us a different way of using techniques from standard calculus or mathematics in order to show this, rather than to hunt for this algebraic simplification and hunt for these constants. This is a different way of showing these properties. So let's do some limit examples. So supposing we have, as we have, so n minus n into n minus 1 by 2, and we have n squared. Okay. So now we have seen before by a direct calculation that this is actually the relationship here is theta. That is, this is theta of n squared. Okay. Now if we do this limit calculation of n into n minus 1 by 2 divided by n squared, okay, then we can pull out this half factor. So we get half. So this is just simple algebraic simplification, n into n minus 1 by n squared. Now we can break this up. So we get half limit n tends to infinity of n squared by n squared minus n by n squared. Okay? So this cancels. So this is 1 and this is 1 by n. Right? So I have limit n tends to 1 minus 1 by n. 1 by n tends to 0 as n tends to infinity. So this goes to half. And so this is some constant c greater than 0 which is finite, and therefore this establishes that the two functions are of the same order of magnitude. So let's look at another example. So supposing we want to compare log of n and square root of n. Okay. So now we take this limit again as n tends to infinity of log of n divided by square root of n. Now here we can use some calculus trick. So we can use the Hopital's rule and differentiate the top and the bottom, right? So we can take this thing and differentiate it. And if we differentiate the top and the bottom, then we get something like this. We get log of e times 1 by n divided by 1 by 2 root n. Right? So you can check that this is the top is the different derivative of the top and the bottom is the derivative of the bottom. And if we simplify this, okay, we'll get 2 log e, because this doesn't depend on n outside. We get this limit as n tends to infinity of root n upon n. Okay, and this actually goes to 0. So since this goes to 0, this shows that actually log 2 of n is smaller than square root of n. So this is actually big O of square root of n. So as a final example, let's look at these two big functions that we looked at last time, n factorial and 2 to the n. We said in a loose sense that both of these are very fast growing, they're exponential, and so they will not be useful for any algorithms beyond very tiny values of n. But we can actually differentiate these to some extent from each other by saying that in the limit, if I look at n factorial by 2n, now these are kind of different types of functions, so I can use what's called Stirling's formula and approximate the value of n factorial as square root of 2 pi n times n by e raised to n. Okay, so the numerator I've used what is called Stirling's formula. And now once we have Stirling's formula, the rest follows quite easily. We can just do some simplification. We can simplify this whole thing and we can get limit and we can pull this numerator factor out. And now we have n to the n, e to the n, 2 to the n, so we can simplify this whole thing as n divided by 2 times e the whole to the n. And now what's going to happen is that this term is going to go to infinity. So the answer is infinity. So actually, so this says that really speaking, n factorial is well above 2 to the n, but for practical purposes we call n factorial also exponential because it actually grows very fast as n grows, but 2 to the n is much slower than n factorial is what this tells us, because n factorial over 2 to the n, the limit tends to infinity. So what we have seen is that we can use limits to compute big O, theta and omega. So the idea is that we take the limit as n tends to infinity of this ratio f of n by g of n and see what happens. So we could get a limit of 0, in which case f of n is smaller than g of n. So we could conclude that f of n is O of g of n, which as we have seen before is the same as saying that g of n is omega of f of n. On the other hand, if the limit is infinity, we have the reverse. So we now say that f of n is actually omega of g of n, which symmetrically is the same as saying that g of n is now O of f of n. And of course, we could find that we get a non-trivial limit c which is bigger than 0 but which is finite, and this really says that f of n and g of n are the same order of magnitude. So we get f of n is theta of g of n. And in rare cases, we might find that there is no limit defined, in which case we can't do anything. So to conclude our discussion about asymptotic complexity, let's look at some typical examples. These are examples of the type of functions that we encounter when we analyze algorithms. The first case could be that t of n is a constant. So it is some constant times 1, so we write O of 1 for a constant. And if it is a constant, really the running time is independent of the input. And if it's independent of the input, it means that it doesn't depend on n at all, and hence it's a constant. But as you can imagine, an algorithm which doesn't even read its input is not very useful, so this is rare. The next useful class that we might consider is an algorithm which runs in logarithmic time. Now this is something which actually we are quite familiar with even informally. An example is binary search. When we look for a value in a dictionary or some kind of a sorted list, so what we do is at each point we focus on the midpoint and look left or right. So we divide the space by 2. So if we keep dividing by 2, then in a logarithmic number of steps we come to an interval of size 1 where we can either say that we have found something that we are looking for or it doesn't exist. So in general, we might divide not by 2 but by some other constant k, so divide the problem into k parts, and this you can check will converge in log to the base k of n steps. A third category which is common is linear. So we say t of n is O of n. This is the linear set of problems. So in these problems, you essentially have to scan the input, but scan it a fixed number of times, typically once, but maybe twice or thrice, but the number of scans doesn't depend on the length of the input. And an example of this is one which we already seen If you recall, we looked at an algorithm when we were defining best case, worst case, and so on. We said what happens when you search for k in an unsorted array A. So since the array is not sorted, we begin at the first element and move till the end looking for k. If we don't find it, then we have to scan the entire array. If we do find it, we can exit when we found it. But in general, the worst case complexity in this case would be linear if we have to scan the entire array. The next class is n log n, and this is typically what we find when we have some kind of efficient sorting algorithm. And we will see that the technique that achieves this is something called divide and conquer. So unlike binary search where we divide but we only look at one part. So if we are doing a binary search, we are searching for something in a dictionary, we can ignore the half where we know it doesn't lie. We pick a midpoint, look at the other half. Whereas in divide and conquer, you have to actually solve both halves. So when you have to solve both halves, instead of log n, you get n log n, and this we will see in detail later on. A quadratic algorithm is something which basically has two nested loops. So when you're comparing all pairs, for example. So a naive sorting algorithm, as we saw in the first lecture, would compare every pair to determine which is bigger, or the naive algorithm to compare distances between every pair of points in a region. So these will be n squared algorithms. Of course, the next step would be a cubic algorithm. Okay, so this will typically have three nested loops. And many algorithms in linear algebra which manipulate matrices. Okay, so if you take n as the dimension of the matrix, then typically you will have n squared entries and you have to do some linear number of passes, and that will give you an n cubed algorithm. And finally, we have these very large cases, either exponential, okay, or factorial. So the first case typically arises when you try all possible combinations, so all possible subsets. So supposing you're looking for the optimum way to fit some group of items into a box, then if you pick every possible group, every possible subset and try it out, then you will have an exponential algorithm. And factorial comes out of permutation. So if you have to rearrange something or you have to count some ways in which you can choose things, if you have to try every possible permutation, then it will be a factorial algorithm.